Okay, so add at index is today's homework, right?
Yep.
All right, so we've been working on our linked list, and last time we wrote our remove at index. So now we want to add something at index, and we drew some pictures last time. So we're going to start off kind of with that. I'm just going to reconnect up our list here a little bit. Actually, we'll leave it like that. We'll call this guy the dude to add. All right, so we'll skip pre-dude for right down. All right, so for dude to add, when we add something, we want him to become the new whatever index we said. So let's assume that right now, that's what our list looks like. Bucket 0, bucket 1, bucket 2. Okay, and we want to add this guy here ultimately at bucket 2. And actually, for this example, I'm going to make him at bucket 1 because bucket 2, we'd say, oh, he's going to be the new last element. Although actually he wouldn't be, so it wouldn't make any difference. 1 or 2 is the same algorithm here. All right, so there are 3 elements in this list. So if we say added at bucket 3, he becomes the new last element. So we would say just call add last or add end, whatever we called it. If we said bucket 0, we would call our add front. Anything in between those, we have to go and find out the guy that comes right before him, right? So if I want to put this at bucket 2, I need to start at the head of the list, move until I'm at the guy right before bucket 2. So I want prev-dude to be the guy right before bucket 2. So let's go over here and add some code in. All right, so we're going to write, first we need to add it to our header file. So this will be void added index. And we're going to take an int payload or an int value and an index that we want to add it to. So now we want to go implement this guy. Okay, so we have our added index here. So we'll go ahead and ask a couple questions. We're going to say if value is equal to 0, and we can assume that they'll go ahead and give us a legal index for our example here. So if they gave us a 0, then what we're actually going to do is just add it to the front. So we'll say this, add front, that value. Oh, thank you. Else if value is equivalent to this count, then we'll say this add end value.
Okay, would you want it to be if index equals 0? Or is it
Oh, index, thank you. Yeah, if where I'm putting it is 0, add it to the front. If where I'm putting it is equal to the count, add it to the end. Else, we want to put it somewhere in the middle. So we're going to go ahead and create our node. And by my picture here, I'm going to call it dude to add. All right, so we're going to create a node pointer here called dude to add. And this is going to be a new node pointer passing it the value. That's the new guy that we're going to add to this list. Okay, so that line right there creates this picture for me, that guy right there. All right, so now I need to create a pointer that starts off at the head of the list and moves up until we get to the node immediately before the guy we're adding. Now, if we're in this else, we know we're not adding to bucket 0, and we know we're not adding to the end of the list. So we know we're somewhere in between, meaning that we are somewhere that has a before, and we are somewhere that has an after, right? Both of those things are true. So we're going to start previewed off at head. So I'll go ahead and create a node pointer previewed, and we'll set him equal to this head. All right, now we need to walk him to the bucket before index. So if I'm adding this guy to index 2, for example, I want him to be the new 2, I'm going to go from this to this, and then I'm done. I'm going to do something one time. So that means index -1 is the number of times I'm going to loop through. So I need to say for I is 0, I is less than index -1. So if index is 2, index -1 is a 1. Is 0 less than 1? It is. Jump, increment the 1. Is 1 less than 1? No, I'm where I want to be. So we'll go ahead and write our loop that takes previewed to that place. For int I is equal to 0, I is less than index -1, I plus plus, previewed is equal to previewed, get next node. So that'll walk previewed down the list. So that'll, in our example here, if we're trying to add an index 2, that will get previewed pointing right here. Okay, so good.
Just want to make sure I'm pretty good understanding, but these nodes don't actually have indexes.
Correct. Yeah, we're imagining that a list, our collections are 0-based indexes, just like an array is or something like that. Yeah. That way we're being consistent, because nothing says that we can't have these guys indexed however we want. We just happen to be consistent with programming languages tend to have 0-based index collections. So it's a thing. Yep. And really, for those of you online, the question he was asking is, these nodes aren't actually keeping track of what their index is. They could. It's not a great reason not to. We might be interested in a node perhaps knowing where he is in the world. I'm not sure how we'd use that right now, but certainly we could keep track of an additional piece of information. But as I have it displayed here, all these little green boxes, these are for kind of human eyes only to represent that this is bucket 0 of our list. This is bucket 1. This is bucket 2. This is going to be our new bucket 2, which will make this guy bucket 3. But it's purely from a how we are understanding it. And also keep in mind is this does not dictate. I mean, this could be memory address 31 here. So just because I'm saying this is bucket 0, bucket 1, bucket 2, that has nothing to do with the order of memory. That's the advantage of a linked list, is linked lists are arbitrary in size, and we add and remove nodes as we need them. And we don't know what else is going on in the computer in the background that might free up some memory earlier in memory than our bucket 0. And the next time we ask for new memory, when we create our new node, it says, yeah, here, I found you some memory right there, memory address 31, which technically is lower than all the other memory addresses. But it doesn't matter, because head points to this guy, which then points to this guy, which then points to this guy. Doesn't matter where we're bouncing back and forth in memory from. Kind of like airports. If you've ever flown from Milwaukee to LA via Atlanta, so something like you go the wrong direction and you go back the other direction. That kind of stuff. Okay, so we have our prev dude positioned at the right place. That is the guy that's right before what the new guy should point to. So now we need to make sure that we do the right thing. In this particular case, tail already points here, but for this example, let's pretend like tail doesn't point here because we just happen to be near the end of the list. And that's why we see tail. Okay. And what I mean by this is this. If I'm already pointing at prev dude, and I know this is the guy that's going to be before the guy we're about to add, we might be tempted to do this. Make prev dude point to the new dude that we're adding. The problem with that, though, is we just lost this guy in memory. Right now, tail happens to point at this one, but that was just sheer luck, right? That we were close enough to the end of the list that we didn't actually lose them. But generically, the generic algorithm idea behind this is we just disconnected the lifeline we had to the next guy in the list. So we can't make this guy point to the next guy, to the new guy yet. Instead, we have to make the new guy point to the same place as prev dude's next node. Okay, so we're going to make dude to add. We're going to set his next node equal to prev dude's get next node. So they both point to the same place in memory. Dude to add, set next node to prev dude, get next node. Okay, so that line right there corresponds to this ninja move. From here to here. Dude to add's next node is equal to prev dude's get next node, which already points here. So now they both point to the same place. Now I can disconnect prev dude and make him set his next node to dude to add. Good.
So if we did that in the opposite order, then 7 would index 1 would point to 2, and then 2 would set it to itself.
What do you mean if I did it in the opposite order?
So like if you had done it how you said not to do it.
Okay, so if we go down the rabbit hole here, if I said this, if I said prev dude set next node to dude add, and now my intention is to set this guy to this guy here, but I have no way of getting at that guy. So it's not that prev dude gets set to himself. It's literally I no longer have the ability to reach. He's floating out into space. I can't get to him because nothing links to him anymore. All right, so we're at this situation where we have prev dude's next node pointing to the same place as dude to add's next node, which then allows me to say my final ninja move, as I put it, is set this guy's next node to the dude to add. Prev dude set his next node to dude to add. Not dude to add's get next node, but dude to add himself. We want prev node's next node to be this new node that we're adding. And then that new node that we're adding already now points to what prev dude used to point to. All right, and then to his point, now we can update in our mind the indexes of our list. This is now the linked list we have. This thing links to this, links to this, links to this. So in reality, it's bucket 0, bucket 1, bucket 2, bucket 3. Okay. All right. So that should be it for added index. Do need to increase the count. And again, just like last time, we only want to increase the count inside this else, because if we're relying on add front or add end, those guys are already doing the count plus plus thing, right? So we'll say this count plus plus. Oh, I don't even have my camera on. People aren't seeing how amazing I look today with my Ninja Turtles. Oh, and once again, the whole Ninja Turtle stuff is fair game for final exams and stuff. Like color bandanas, the weapons, the names, the whole rigmarole. In fact, it's probably going to be as much as 80% of your exam. Does anybody know who my favorite Ninja Turtle is? Nope. You had 25% chance. Why would you think Raphael? Oh, just I had a 25% chance I threw a dart.
That's what I do on exams.
Oh, it's Donatello. He's a smart one. I like the, huh? Purple one, yeah. He's like the inventor. He's the smart one, gadgety. Bow staff, yep. Michelangelo's nunchucks. I guess he just likes to party. Pizza guy. Raphael's like the strong one. Red bandana, the size. Orange was Michelangelo. Leonardo's blue with the katana blades. He's like the leader. He's the leader. He's probably my second favorite. The funny thing is Michelangelo, because my name is Mike, you think that, oh, those, no, he's close to my least favorite. It's really a tie for who I like the least between Raphael and Michelangelo. I respect Leonardo, but I like Donatello. Okay, so all this fair game for exams. Just I am recording. Just go back and review. So actually, here's a hint on how to get better partial credit when you're completely clueless on a question. I'm not promising this. It just depends on the mood that I'm in when I'm grading. But if you're clueless on a question and you're like, okay, I really don't know what I'm doing here. Here's some Ninja Turtle stuff. You can get some points is what I'm saying. Sometimes they get nice little stories written in there that are pretty funny. And if it makes me laugh, then I'm, you know, I mean, it's not worth a lot of credit, but it might be worth something. But you start naming variables after Ninja Turtles and stuff like that, maybe I'm a little bit more generous on another question on the exam or something. But that wouldn't work because I grade the exams with the names off and I grade all the questions. So I grade all of question 1, then all of question 2, and so on and so forth. That way I'm making sure I take points off and stuff, can try to do it consistently. Like, why did one person miss 2 points, another person miss 3? The chances of me having inconsistencies like that when I'm grading all of the same question in one fell swoop is lower than if I'm grading your whole exam and then his whole exam and so on and so forth. But Ninja Turtles will never make your grade worse. That's a promise. that is, you can take that to the bank. Okay, so question, let's test it, but when does my code ever break? Come on. I literally just heard what Emily was thinking. When I said, when does my code ever, she is here, isn't she? Because the joke breaks if she's not.
She's actually
Oh, that's the way it goes. Which makes it even worse. She telepathically heard the lecture, and then I heard what she was thinking when I said my code never breaks. All right, so let's, what do we got here? Yep, this is our code. So we'll go ahead and do compile. We'll see that it compiles. We need to go ahead and add the use of our function into our driver. So let's go back out here to driver. And here, let me just do a quick display. I'll run this. All right, so my list currently looks like this: 17, 13, 4, 8, 2. So if I say I want to add a 6 at bucket 2, my expected result would be a 17, 13, 6, 4, 8, 2. So we'll do an LL add an index, add index, and we're going to add a 6 add index, what did I say, 2? And then we'll do LL display. All right, so our expectation is to get a 17, a 13, a 6, 4, 8, 2 as our last one. 17, 13, 6, 4, 8, 2. Okay. So obviously we have tested this thoroughly through hundreds of iterations. Code obviously perfectly works. All right, so questions about that for added index? All right, not too bad. Okie dokie. So let me go ahead and push that. Hopefully, I think added index is a little bit easier than remove an index, but certainly added index doesn't feel too bad after you've seen remove an index. But hopefully we all kind of appreciate that. Anytime we're working with the middle of a linked data structure, things get a little more sketch because we got to kind of make sure we don't lose pointers to things. You know, and this kind of falls into that category of why pointers are somewhat scary. You know, even though they're just numbers that kind of like, I'm going to remember this guy, and this other variables, I'm going to remember this guy. I don't want to lose track of either of you. So I can't forget about that guy and let him float off. Somebody else has to remember before I let that happen. So it's just a lot of hooking up wires. You can think of it like that. So as long as you can kind of move your mind away from scary hexadecimal values and really think about them in terms of what they mechanically are doing, it's really not bad. It's not any different than some of the problem solving you've just done as a human being your whole life. You just have to get past the intimidation of hexadecimal numbers and, you know, like, oh, memory seems scary type thing. All right, so let's see here. I'm just going to push this, right? Okay. So let me go back in here. Before I go to stack, we want to do something terrifying. So I promised you a hard assignment over the weekend, right? I thought I did. All right. He's like, yeah, you did. All right. We'll see. We'll see what we end up doing. Let's go back and remember one of our buddies from 250. Remember insertion sort? All right, so, you know, we looked at some sorting algorithms. One of them was called insertion sort. And, you know, if we kind of remember, let's draw a little picture here. I need to hide this. You think you didn't like it before? Wait till you do it with linked lists.
Oh, I'm really not excited.
Imagine the surgery needed to do a swap. Great. All right, so let's say we have like a 2, and I'm going to do these with indexes.
Insertion sort was the recursion one.
No, that was merge sort.
Oh, thank God. All right, we're fine.
But no, you actually bring up a good point.
No, I don't.
You're right. That could be the next assignment. Okay. Or, wait a minute, we might finish insertion sort in class, which then indicates that we could do merge sort for the homework. Merge sort was so much fun.
There's never been an assignment in any class that I've had where I did recursion and I had a good time.
Really? Oh, are you taking 470 in the fall? 470 is the language theory class. I promise you after that class, recursion won't bother you anymore. Because we use a language in there called scheme, and scheme doesn't have loops. So in order to mimic a loop, you have to do it recursively.
I'm gonna drop out of the major.
It's very similar to pointers, and this thing is recursion seems difficult because it's kind of cryptic to wrap your mind around. But when you do it enough times and you start kind of just seeing how it works, it's actually just as easy as any of the other stuff. It just feels unnatural the way you think. You know, this goes way back to CSC300 when I said that programming is not the difficult thing. Python is not the difficult thing. It's retraining our mind. We've been thinking as human beings for, 18, 19, 20 years of our lives, right? That's hard to deprogram. So to kind of start thinking about things in, the kind of the idea of how programming works, how we have to speak to a computer is a learned skill. It takes practice to do that. But once you've done it enough times, you start thinking that way. In fact, one thing I've seen coming out of 470, like right now, you probably feel like, oh, writing a for loop that goes through something 10 times is not a big deal, right? But recursion scares you. When you come out of 470, recursion's not going to scare you anymore. But you might have to, what you'll end up doing is you'll start seeing the solution to every problem recursively. And you're like, well, how would I do this recursively? When recursion's not better than iteration. Just sometimes it's the right tool for the job, right? So you'll come out of 470 and you'll go back to write a program, and something that you used to write a loop for, your mind will immediately jump to a recursive solution for it, even though the correct solution is a loop. So you'll actually, break your mindset, and then you'll reset, and then both of them will be comfortable to you. I promise. That's in my opinion, 470 is where computer science finally kind of comes all together for people. You see all the what's under the hood and stuff. All right, let me make this guy green. So let's say we have a 2, a 7 at bucket 1. I'll copy this. And we'll say we have a 1 at bucket 2 and a 4 at bucket 3. All right, so we're going to, that's our current array, let's say. So we have a, maybe a variable called AR. And AR holds a pointer to the beginning of this list. Okay, so we can think of this as our linked list if you want, but let's just do the algorithm first, and then we'll look at it as a linked list. All right, so the insertion sort algorithm says we keep track of a starting point, cur start. And cur start is going to start off at bucket 1. And the idea is that we try to get this guy moved up the list as far as possible until he's in his final resting place for right now. All right. So we say, should cur start, should a 7 come before a 2? No. So we're done. All right. So we're done with that iteration through. Increment cur start. Should a 1 come before a 7? Yes. So we need to swap them. So we swap the 1 and the 7. And cur start follows. Sometimes when I write this, I call that variable the follower. Is that what I did when I taught it to you guys? Did I put the little skull? Oh, yeah, I like the skull. Actually, you're right. We are going to do 2 separate variables because we can't change cur start. We're going to have follower. We're going to give me the let me go back to the beginning because we do need two separate variables. So cur start's going to start off at bucket 1. We have a variable called the follower. This is the guy we're allowed to adjust that follows something towards the front of the list. So previously we said, should a 7 come before a 2? No. So what do? We increment cur start and reset the follower. Then we said, should a 1 come before a 7? Yes. So we swapped. What happens is the follower follows. We keep going as long as the follower, as long as we need to swap and the follower is greater than bucket 0. Because once we get to bucket 0, there's nothing before. I've gotten as far as I could go. So we are not at bucket 0, so we can check the guy before me. Should a 1 come before a 2? Yep. So we swap. Follower follows. Now we're at bucket 0, so there isn't a person to check beyond this. So we're done. We increment cur start, reset the follower, then do the same thing. Are we at bucket 0? No. Should a 4 come before a 7? Yes. So we swap. Follower follows. Should a 4 come before a 2? Nope. So we're done. We increment cur start. It's off the end of our list. So now we're done and our collection should be sorted. 1, 2, 4, 7. Okay. Remember that guy? Insertion sort. All right. So now go ahead.
Would you say the best way to do it is increment cur start and tail end it off the list, or could you just do a full list that just goes from the
Oh, you would do cur start in a for loop. Yeah, bucket 1 to and you'll keep going as long as cur start is less than the length. Yep. So why don't we go ahead and just write this function using a normal array as a quick example. Okay. Over here. So we'll just do this inside of driver. And I'm going to go ahead and we're just going to create a function down here called void insertion sort. And this guy is going to take a int array called AR. Actually, in C++, it's that. And we also need to pass along the size, the length of our int array, because arrays in C++ aren't able to report their length themselves. All right. And now we'll go ahead and define our a couple of our variables. So we'll say we're going to need, and we're assuming we're working with an array of integers here. So we need an int temp. We'll call this guy temp swap. He's going to be used for doing our swaps. Then we're going to have an int the follower. And this guy is the guy that will follow. We'll have our for loop for int I is equal to 0. I is less than the length. That's the number of elements in our array. I plus plus, and actually we can call this guy cur start instead of I. Okay. So now each time through, we want to ask a question. Well, we first need to reset the follower. So the follower will be equal to whatever cur start currently is. Then we want to keep doing something as long as, so we're going to repeat something over and over again, as long as 2 conditions are true. The follower is not at bucket 0, and the value that comes before bucket the follower is less than the value at bucket the follower, meaning we should swap. So while the follower is greater than 0 and AR at bucket the follower is less than AR at bucket, the follower minus 1. This says I'm not at the beginning and I should swap. If that's true, what do? I swap. I say temp swap is equal to AR at bucket, the follower. AR at bucket, the follower is equal to AR at bucket, the follower minus 1. And then AR at bucket, the follower minus 1 is equal to temp swap. So we preserve AR at bucket follower, overwrite bucket follower with follower minus 1, then overwrite follower minus 1 with what we had preserved. That does our swap. And then what happens? The follower follows. Okay. So we'll do that over and over and over again. And when we're done, our array should be sorted. We're going to come up here. I'll go ahead and just comment this stuff out for a bit. Have we done random numbers in C++ yet? Okay. I think it's rand.h. I think it's rand. Generate pseudo random bytes. Standard lib. Here we go. We have something called random. So it's in standard lib.h. That's where it lives. We have a function called random that returns actually what's called a long int. So this is a extra big number. Whatever. Well, but it's a non-object type. So in Java, we have something called big integer. And big integers in Java are actually implemented as linked lists. So or they're likely implemented as linked lists, at least. I guess I'm not positive. So that allows you to have an arbitrary size value. Okay. But the larger the value gets, the less the less efficient it ends up being in terms of speed. You start doing math with some gigantic value. Functionally, you can make it work, but if that value is 7,000, links long to represent your number, things can get, problematic pretty quickly. All right, so we're going to use this random function here, and I'm pretty sure that random function is going to give us a value in the range of all values, range of all integers. So I'm going to come up here, I'm going to do include standard lib.h. And then I'll just go ahead and say int val is equal to random. This guy actually says it returns a long. And then let's just do a cout val. So we'll just generate 10 values real quick and display them. Let's just see what they look like. I'm thinking they'll be both positive and negative numbers in the range of all integers. We got positive values there, so just run it a couple. Yeah, I'm running it multiple times though. Although, notice something here. This is actually an interesting thing. Notice we're getting the exact same random numbers each time. And the reason for that is The random number generator in and Java used to have this problem. You have, when you're dealing with random number generators, you have this thing called seeding. You can seed the generator with a kind of a starting point. And a lot of times with the random number generator in C++, so let's do man random, we have this thing called sRandom, which is an unsigned integer. So we can call it sRandom, passing it a value. So I'm going to go in here, and before we do anything, we'll go ahead and call sRandom. And, you know, we're going to pass it some value. So right now I'll pass it a 5, let's say. No good reason, just I picked a 5. Make sure I save this. So see, we did get different values than our original values there. But notice we're still getting the same values because we're seeding it with the same hard-coded number each time. So then the question is where is our source of randomness for getting a random seed value? Okay, and a lot of times this will come from, I think it's time.h. Let's see. Or it uses dev random. Let's Google it real quick. All right, time null. So we're including time.h, and we're going to seed this guy with a random number where there's a function called time, and we're going to pass it the null value, and it's just going to give us, I'm thinking time either gives us the current number, the current milliseconds since 1970, which is something called the epoch, but it should give you a ever-changing value is the idea. So there's that. Now when we compile and run it, we should get different random values each time through. Notice that sometimes I run it too quickly. I get the same number a couple times in a row because time returned the same value multiple times in a row since I ran it fast enough. So whatever, that actually probably tells me it's not the number of milliseconds. It's probably a less granular time period. Maybe it's, I don't know, hopefully not seconds, but whatever. We got more randomness now from this guy. Just kind of an interesting thing to point out. If you ever work with random numbers, depending on the language, you might run into a situation where you're always getting the same collection of random values. So that no matter how many times you test it, you're always getting the same stuff. And so this is more just trivia information for you that, hey, this could be going on depending on the language you're working with. So you might need to seed the random number generator. Okay, so let's go ahead now that we have this. Let's go ahead and create our array of values. Now I can, it looked like they were all positive numbers, right? So I can go ahead and say val is equal to val. How do I make val, which is between 0 and some giant number? How do I make it between, I don't know, 0 and 1,000? Yep. Which would make it, so val equals val mod 1,000, which would give me 0 to 999. 1,001 would give me 0 to 1,000. Doesn't matter. Same deal. So we'll say 0 to 1,000, and well, this will be the numbers between 0 and 999, or if I want it to be 1 and 1,000, I could just add 1 to that. You know, whatever, however you want to massage the value into the range that you wanted. But this will give me, you know, better values, let's say, or more easily recognizable values. Go ahead.
So Java has like, you can either get any number of things together, or you can get like,
Yeah.
whatever you want to use as it. Does C++
Well, the random function didn't look like it did. I saw the other thing was using something called rand. Let's see. That's for seed. Yeah. I mean, the short answer is I'm positive there's a library out there that does it. It doesn't look like one of the core built into, has been around forever, does that. But yeah, I mean, it's nothing special about it. It's behind the scenes just doing the same crap we just did. Yeah.
For the rand function, there is a library.
Well, that goes from a range. You can say, give me a number between 5 and 30.
Or it picks a random number within a range.
Yeah, that's what he was saying. So, yeah, probably. Yeah. Yeah, but I mean, those are good questions because I mean, that's something that we do, that is a difference between something like Java, which kind of has a standardized collection of things, right? And Java's platform independent. So whether you're writing in Linux, you're writing in Windows or Mac, whatever, if you're doing Java, Java is Java. So their random class has the abilities it has. Whereas with C++ or C, we're at the mercy of what's available to us from the operating system. So here we have time.h. Where on Windows, I'm sure there's a time library, but it might not be called time.h. It might be named something a little bit different, or it uses different system calls, whatever. The random number generator over there, I would be surprised if Microsoft doesn't have a random number generator that has a range, because they're operating kind of a much newer world. So they built their C++ development stuff on top of, you know, the old school C++ core language, but in terms of the Microsoft stuff that was available to them. All right, that makes some sense? Yeah. All right, so we should get numbers between 1 and 1,000 now. Just make sure that's the case. And I'll just connect one more dot here. This goes back to, we really harped on it last semester, but talked about it some with Python, is the power to be able to read documentation. That was the thing with Java where we hit it so hard, this idea of static versus non-static methods, and what does it mean, and how do you call them, and how do you write them, and all that stuff. Because one of the skills we need to have as developers is we got to go be able to read documentation and say, okay, I need to use a tool. It's no different than walking into Home Depot and you're looking at hammers and you want to find out, I know there's not that much difference between hammers, but they have a lot of different hammers on the shelf. Okay, so you're looking at some equivalent products. You want to find out, well, what does this one do that this one doesn't? That kind of stuff. So one of the abilities we want to have is being able to read documentation, because we're not going to have these languages memorized. So I'm like, okay, well, we, I want to use random something. I kind of remembered it was random. I started with old school Google with the man pages, right? And then I said, I know I need to seed the value. How do I get a source of randomness? I think it's time something. It's just from leftover from memory at some point. Then we, the new cool kid is Google, right? You hit Google and, try to find a library that does that. But with C++, we have to marry it to the OS for a lot of that stuff, because it's talking at closer to the OS level, whereas Java is talking to a virtual machine. So it wrote the thin OS that lives between that and the CPU. But in any case, reading documentation and being able to understand it is far more powerful than the amount of a language you have memorized. All right, so it looks like we have random numbers between 1 and 1,000. That's looking decent. All right, so our goal here now is to get that guy sorted. Okay. Now, one interesting thing here. So I'm going to go ahead and I'm going to create a int AR array. We're going to do 10 values in here. And I want to just print something out here. I'm going to say cout size AR. I'm pretty sure. Oh, size is not a thing. Is it just size? Oh, it might be size of. I want to see if that gives me a 10. I think it will. Which is interesting. Why did it give me 40? 4 bytes. It's 4 bytes. So an int is 32 bits. So it gave me 10 4-byte chunks. So if I want to then get I can say size of AR divided by size of int, and that will give me my 10. So we can calculate the length of something if we wanted to. Does that make sense? We could also just write a quick function that does this, and let's just go down that rabbit hole. We say, oh, that might be something that's handy. So we'll go ahead and write a function. So we're going to say void. Actually, am I able to get the type of a array? I wanted to write it fairly generically where I can say what kind of value is stored in this array and what's the size of that value. So I could have a function that I could pass it any array and it would give me the size of that array. Get type of void pointer. Oh, actually, I could just get the size of the value that's there. All right, let me try something here. Void, call this guy get length of array. And this guy is going to take I think I can do that. Actually, it's going to take in a void pointer AR like that. And I'm going to do, I'm just testing something here. I'm going to say AR size of AR at bucket 0. The value at AR, the base address, value of AR. Can I not take in a generic type? Oh, well, I won't kill it. One way or another, we could probably hammer this out. Basically, what I'm trying to do is I'm trying to write a function that will take in any kind of array. And I can then ask, how many bytes are you? And how big is each of your elements? So I can return the number of buckets that are in that array. If we presume, like we could certainly write it for an int array, right? We just saw what we did above there. But for right now, we'll just go ahead and, well, here, actually, we'll write it for an int array. Get length of int array. This guy will take in a int array AR, and he's going to return an int, which is going to be the length. And we'll go ahead and return size of AR divided by size of AR at bucket 0, which should be an int.
And in this case, size of AR is going to be 4, so you could just put in 4 if you were only.
Yeah, or actually we could just say size of int instead of hard coding a 4. We could just say size of int. So this will be get the length of an int array. So we're filling our, let's go ahead and write a display for an int array too. So we'll say void display int array. This will take an int array AR. And we'll go ahead and say for int I is equal to 0. I is less than get length of int array, and this might be where we need to prototype some stuff, but I think we'll be okay here. Get length of int array, passing it AR, I++, and then we'll do a cout AR at bucket I and L. So after I've created my array up here, I'm going to go ahead and fill that array up then right here. So we'll say AR at bucket I, and we'll call this guy get size get length of int array. And we're going to pass this guy AR. And then we'll say AR at bucket I is equal to our changed value. And then afterwards, we'll call display int array, passing it AR. And we should get the contents of our array. All right, so this is good. So notice here it's saying this was not declared in this scope because I declared all these functions at the bottom. I'm trying to use them ahead of them. So the old school way would be to prototype them at the top. The newer school way would be to put these guys inside of a header file so we know about it. I'll just quickly take our couple of functions and prototype them so you can see what's happening. So what it's saying is like, look, we know we wrote that function. But we also, at the time, if I'm in the middle of main here, and I'm trying to call get length of int array, and get length of int array was not written until down here, that's a problem.
So this is error.
I believe it gave me an error. Yeah, these are errors. Let's see, size of an int pointer. Oh, so this is giving me, well, no, we got 10 when we did the size. We got 40, the total number of things in there. I think this warning might be incorrect because it's saying size of on AR, this guy right here, will give you the size of an int pointer, size of a memory address, not the size of that particular array. But when we printed it above, we saw that it did give us the number of bytes that are in there. All right, I'm only gonna mess with this a little bit longer. This is more important stuff, but more things you might run into as you're working on things. So for right now, I'm going to go ahead and I'm going to steal the names of my functions. We'll just say prototype functions, and I'll just put them all up top here. Ooh. All right, so now I prototype those three functions that I'm using right up top here, and we don't need to worry about their implementations being reliant on each other because I haven't written the implementations yet. So now when I get to main, it'll know about those functions. So there's my compile. I really think it's going to work. I mean, it's giving me a warning, but we printed out what size of did for an array. Why did I get a 68? I found 48. Get a random number, put it in my array, then display that array. So that must have given me a funny value. Okay. Just for our say define array length to be 10. I'll show you something new here. This guy is called a macro. This guy will be size array length. Array length. We'll display our int array, which will go off of our array length. And we'll just get rid of that guy. All right, so there's our numbers. Just a quick thing here. This is not a variable. So macros typically are all uppercase. This just says anytime you find this exact spelling in all caps throughout the code, it doesn't have to be all caps, it just happens to be the naming convention. Go ahead and replace it with a 10. Yeah, because this is I made the size of my array 10. So if I decided I wanted this to be 30 instead, I don't need to change it anyplace else. Now I have a new size array. There's my 30 values. Make sense? But it actually is not an integer. It's not stored as an integer. It's just a placeholder that before compile time will map to the literal value that is that guy. All right, so let me switch it back to shorter. So we'll make it, we'll make it 10. And we'll start off, we'll just run it again real quick. Make sure we see that it's not sorted. So there's our not sorted array. Then we'll go ahead and we'll call insertion sort on this guy. And we actually have insertion sort taking in the array length, but I already have the array length stored, so I can just change my insertion sort to only take in that. And then this guy will be array length in there. I need to change my prototype for insertion sort up here to only take in my int array. So I'll call my insertion sort, and then I'll tell it to display again. And just so we don't get our numbers mixed up, I think we're all convinced it's not sorted before we call insertion sort. So what we see displayed now, assuming we wrote insertion sort correctly, should be the sorted version of our collection. So there's the sorted version of our collection. All right, make some sense? so I don't forget, let me go ahead and do a push. Okay, homework. Based on the normal array version of insertion sort we wrote in class, implement an insertion sort within our linked list class that will sort the list using the insertion sort algorithm. Note, you must use insertion sort and do the swaps. Do not create a new array or a new linked list. Well, I'll just say it out loud. Do not create a new linked list and fill it up with the smallest value, then the next smallest value, then the next smallest value. So, we're good. Then make head point to that guy. Yeah, you can delete it or just make head point to the new guy and be really wasteful and just let the old guy die in memory. It's kind of like, look, so the idea would be if you had the original linked list, you're going to go through, you're just going to cherry pick the low values. So I'm going to find the low value. I'm going to remove you from that index. I'm going to add you to the end of my empty linked list over here. I'm going to find the next low value. I'm going to remove you from that index. I'm going to add you over here, over and over and over again until we have this guy is empty, right? And this is my new updated list. Then I'll just make head point there. Done. Don't do that. Write insertion sort with swaps, okay? Because the exercise we're working on here is still working with pointers, kind of performing that swap surgery. Go ahead.
So do you want to swap the numbers that are in the
No, good question. You should swap the actual nodes, not just the numbers inside a node. Because again, the point here is we want to work with pointers, hooking up pointers, not losing track of nodes, things like that. Okay, don't just cheat and say, well, I got two nodes. They already have their nice happy home in memory. I'll just make this guy's payload value, and I'll just swap the payload values. No harm, no foul. Don't do that. Swap the whole physical node. Since we're dealing with integers, yes. But if you consider where we're going with this, where we maybe are going to be sorting a deck of Hearthstone cards, where now it's you don't just have a simple pass by value type payload. Your payload now is an object type. Right? So it doesn't not make sense, but it doesn't, I'm trying to think of an example where it would be a bad idea. Realistically, it would be okay always, because you're always going to swap the payload value of the nodes and just say, hey, structurally, these nodes are okay. Why move the nodes around when I can just swap the values of those nodes? That's fair. You could make that argument. Here, I'll tell you the downside. The downside is to do that, you would then need to give write access to the payload field. You'd have to be able to set a payload, similar to how we can now set a next node. So we'll say setting a payload could be dangerous because now you're allowing somebody to just change the value of a node. Now, if you wrote the whole program yourself, who cares? That's okay. But for the sake of this assignment, we want to actually move nodes around in memory. So we have pointers that get hooked up to other nodes. So if something gets swapped, it's literally, don't forget about this guy, make him point here, make this other guy point here. Now they've swapped. All right. Questions, comments, concerns, bribes? What's today? Let's do Tuesday. Oh, that's a good question. Do we have class next Thursday? Then let's do next Thursday. But I would, if you want to take advantage of what is break Tuesday, Wednesday? Yeah, so if you want to take advantage of your Tuesday, Wednesday break, you should probably pretend like it's due on Tuesday. So you're done with it. And then you can rest until Thursday instead of stress Tuesday and Thursday writing this code. But, you know, hey, whatever you want.
So just to make sure, the node, like the payload inside of it and the memory address will stay the same at all times. And you're just moving around the-
Correct. Correct. Yeah. A node, once a node is originally created and it has its memory addresses won't change. It's the next node pointers that will start pointing to different memory addresses. Okie dokie. I will see everybody on, I guess, Thursday. I should have signed to somebody to message me on Monday night reminding me we don't have class on Thursday.